Friends, today's topic of discussion is design procedure of flexible coupling. The first part we will design and or find the diameter of the shaft. So diameter of the shaft can be found by using these two formula, that is T is equal to P into 60 divided by 2 pi n, where T is the torque and P is the power transmitted by the shaft and n is the RPM. Using this torque we can use this formula, torque is equal to pi by 16 allowable shear stress d cube. Here we have written S because the shaft is made up of steel, and with this we can find the diameter of the shaft. Once we have the diameter of the shaft, then we can calculate the dimension, okay, related to the pin. That is, the first thing we will find is d1. D1 is the diameter of the pin and the formula is 0.5 d divided by root n, where d is the diameter of the shaft and n is the number of pins. Okay, then d2. Here the pin has this bush, that is brass bush, which is of 2 mm thickness, and then we have a rubber bush which is of 6 mm thickness. Therefore we will find the diameter of the bush as d2 is equal to d1 plus 2 into 2 plus 2 into 6. So this is the diameter of the bush or the diameter of the hole. So then we have to find this length of the bush which is in the flange. So to find that, we will use this formula, torque transmitted by the coupling is equal to W into d1 by 2. Okay, so here d1 we can calculate with this formula, and d1 is the diameter of pitch circle of the pin. So d1 is equal to 2 into d. So d is the diameter of the shaft plus d2, that is the diameter of bush, plus 2 into 6. So now this W, so torque transmitted by coupling is equal to W into d1 by 2. So W is the bearing load on all the pins. So to find that, we need to use this formula, N into PB into D2 into L. So this is W, and N is the number of pins, PB is the bearing pressure on the pin or bush, D2 is the diameter of the bush, L is the length of bush in the flange, and D1 we know that is diameter of pitch circle of pin divided by 2. So with this formula we can find small l. So once we have these dimensions we have designed, now we will see related to the stress. So here we need to find the direct shear stress, okay, which is in the coupling halves. So direct shear stress is equal to W divided by pi by 4 d1 square. So W we know, that is the bearing load on pin, and d1 is the diameter of the pin, and with that we have found the direct shear stress, and then we need to find the bending stress on the pin, so which is equal to m upon z. So we can find m with the formula, that is m is equal to W into L divided by 2 plus 5, where we know W and L, so we can find m, and then we have to find z. So z is equal to pi by 32 d1 cube. So with that we can find the bending stress, but we need to find the maximum shear stress and maximum normal stress. So for maximum shear stress, the formula is half root of bending stress square plus 4 into direct shear stress square. And to find maximum normal stress, the formula is half into bending stress plus half root of bending stress square plus 4 into direct shear stress square. So with this we will have the maximum stresses, and this maximum stresses which it can handle should be less than the given or permissible stresses. So once this is done, now we will design the hub. To design the hub, so here this is D is equal to 2D, where this D is the diameter of this hub. Okay, so D is the diameter of hub, and capital L, that is the length of the hub. You can see this is L. So here D, that is the diameter of the hub, will be 2 times D, that is the diameter of the shaft, whereas L, that is length of the hub, will be equal to 1.5 times the diameter of the shaft. Once we find the dimension, now we will see related to the stresses. So here it is written T, that is the torque, is equal to pi by 16 shear stress which is induced, okay, in the hub, D cube, that is the diameter of the hub, that is D, multiplied by 1 minus k raised to 4, where k is equal to D, small d, divided by capital D. So here it is written C because the hub is made up of cast iron. Okay, so T is equal to pi by 16 induced shear stress, okay, in the hub, D cube multiplied by 1 minus k raised to 4. So here we need to find the induced shear stress in the hub, and here it is written C because it is made up of cast iron. So here it should be less than the permissible shear stress for cast iron. Okay, so then we will find the dimension of the key. So this is the key here. So we need to find the width. Width of the key will be equal to D divided by 4. That is the width of the key. And thickness of the key will be equal to D divided by 6. That is the diameter of the shaft divided by 6, or D divided by 4. So D divided by 6, okay, here D divided by 6 and here D divided by 4. So if we want rectangular key, so here width will be D by 4 and thickness will be D by 6. And if we want square key, then here width will be D by 4 and thickness will also be D by 4. Then it will be square key. Okay, then length of this key will be greater than this L. Okay, so length of the key will be greater than the length of the hub. Okay, then once we have the dimension of the key, now we will see regarding the stresses. So torque equal to W, that is the width of the key, into L1, that is the length of the key, into induced shear stress for the key, okay, in the key, multiplied by D by 2. So with this formula we can find the induced shear stress in the key, and it should be less than the permissible shear stress for the key. So then we will use another formula, T is equal to T by 2, T is the thickness of the key, into L1, that is L1 is the length of the key, into induced crushing stress, okay, for the key, multiplied by D by 2. D is the diameter of the shaft. So from here we will find the induced crushing stress for the key, and it should be less than the permissible crushing stress for the key. So with this we have designed the key. Now we will go for design of the flange. So first we will find the dimension. So for the flange we need to find the thickness of the flange, and thickness of the flange will be equal to 0.5 D, where D is the diameter of the shaft. Then we will see regarding the stresses, and we will use this formula, torque is equal to pi D TF into shear stress on the flange into D by 2. So using this formula we will find induced shear stress in flange. It should be less than the shear stress for which is given or which is permissible. Here also it is written C because it is made up of cast iron.